All right, so let's take a look at our equations really quick. So for our momentum equation, we only have 4, okay? We've dealt with the first 3, and really the first one is momentum, and momentum is nothing more than taking the mass of an object and multiplying by the velocity to find that momentum. Remember, velocity is a vector which needs a positive and negative direction associated with it. And because of that, momentum is also a vector that has a positive and a negative direction associated with it. These next 2 equations are, this is the momentum impulse theorem, but these 2 are the equations we use when we're comparing one object. We're comparing like one object at 2 different locations, like a before and after. So these are one objects. The fourth and final equation we're going to talk about today is the one called conservation of momentum. So the conservation of momentum equation is this. So it's sigma p1 equals sigma p2. So sigma means sum of, p is for momentum, and 1 is really location 1. Or if we're going to talk about, we're talking like before versus like an after. So conservation of momentum is really just saying that all the momentum that we start with, we add up all the momentums of all the objects before, and we're going to set it equal to the sum of all my momentums after the collision. So we often talk about like things collide, collisions. They aren't technically all collisions, but it's just an easier way to say, hey, when 2 objects collide with one another, they interact with one another, what's going on? We use this equation when we're talking about 2 different objects and we're comparing those 2 different momentums. Okay, so that's the conservation of momentum equation that we're going to be using today. In order, before, maybe I should say, before we go too far into how to use that equation, I want to talk about there's 4 basic types of collisions or interactions. So again, they aren't technically all collisions. Like the first one isn't really a collision, but I often talk about just collisions because it's easier to say than like collisions/interactions. So the first type, this is that blue sheet that hopefully you picked up on the cart that we're going to fill in. We're not going to fill it all in today. We're just going to fill in parts that we really care about and need today. Is a recoil collision is when two objects, 2 or more objects, they start together, but they end apart. Okay, 2 or more objects start together and they end apart. And when we say that they end apart, we say that there was some deformation. They're deformed. And really my definition of are they deformed is, do they look identical to the way they started? And the answer is no, they don't look identical, then yes, they were deformed. And if one object starts together and they end apart, then they look different. And that could be something as simple as don't have something better to throw. But if I had this marker in me before and I throw that marker, I look different than I did before. I don't have a marker in my hand, right? So I'm therefore deformed. Hey, that didn't come out quite right. It's deformed because I don't look exactly the way that I did before because I no longer have that marker. When we talk about a recoil, that was an example of a recoil. The marker and I started together and we ended apart. That was a recoil interaction. Now, based upon the speed at which that marker moved and the mass of that marker compared to the mass of me, you didn't notice me like, whoa, I'm getting like jerked backwards, right? But when we talk about recoil, most of the time that what pops to most people's mind is shooting a gun, because they talk about the recoil of a gun. And exactly, that's a perfect example that some people are familiar with and some aren't. But the idea is a bullet starts in the gun. We burn some powder, the bullet comes flying out really, really fast out the end of the barrel. And because the bullet goes really, really fast that way, the rest of the gun goes this way. And because you're holding it, you and the gun like get kicked back, right? There's some recoil. Same thing. We could also talk about a medicine ball, would have been a better example of me throwing a medicine ball compared to that marker. But where if I were to take a medicine ball and I were to throw a medicine ball, we started together and we ended apart. Now, I can take a medicine ball and I can throw a medicine ball and I don't move, right? My body might kind of deflect slightly, but I don't really move. A lot of times when we deal with these type of collisions, we're going to deal with like a idealistic, like no friction environment. So we'll kind of address one with that medicine ball idea a little bit later. I like to draw pictures, and you probably have noticed by this point in the school year, I'm not really good at drawing, but I can do boxes okay. So when I draw boxes or draw these collisions, I often just draw boxes with letters. So because those objects start together, I just draw like object AB. So there's two boxes, but they're together as one. But then afterwards, they're apart, so now I have two separate boxes. That entire column that says, is momentum conserved? The answer is going to be yes, 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 which really just means that I can use that conservation of momentum equation that I've listed on the board. That's what that's going to mean. That last column is kinetic energy conserved. We're not going to deal with today. That column is really used to differentiate between the last two. Now, the names of the collisions and interactions that we are calling these are slightly different than they call them in traditional and AP physics. So just so you're aware of that. I don't think traditional is doing momentum yet, but the idea is we use slightly different terms. So when we talk about inelastic, an inelastic collision is really the reverse of a recoil collision. Okay, it's the reverse. So in a recoil, they started together and ended apart. In an inelastic collision, they start apart and they end together. The way I think about inelastic is if something is elastic, I think of it very stretchy, bouncy, where inelastic is the opposite. So if I were to take like a lump of clay, and I took that lump of clay and I threw it at the board and it went splat, that's an inelastic collision. They stuck together. You're driving down the road and that June bug goes on your windshield in the summer. Yuck. Okay, that's an inelastic collision. You and the June bug are now moving down the road together as one object. And yes, the June bug is deformed in the process. But an inelastic collision could be that medicine ball example again, but instead of me throwing the medicine ball, I'm now catching the medicine ball. Started apart, we're ending together. So my pictures just really flipped from the recoil, because that's really all they are, right? So they start as two separate objects, but they end up together. One of the problems we're gonna do together in class today is where a semi and a car collide and they lock bumpers. So they get stuck together as one object and they move off together. Okay, and the reason why we're gonna do a problem like that is on your virtual day homework, that's one of the problems is where they lock bumpers. Now I'm gonna be honest, most of the time when two cars collide, they don't lock bumpers, they bounce off of one another. And in those situations, it's for today, we're just gonna say it's one of the last two. Okay, it's one of the last two. It's either an elastic or a partially inelastic, and we are not gonna differentiate between the two today. In both of those, the objects start apart and they end apart. So there's two different kind of, like visually, there's two kind of types here. There's one type of start apart, end apart collision that we could think about is the game of pool. So we're gonna play a game of pool, and I take the cue ball and I hit it with the cue ball and I hit the 8 ball. They start apart, they end apart. That visually would be like an elastic collision. A different start apart, end apart would be, like I said, two cars collide, they start apart, they bounce off of each other, but they don't really bounce off of each other, they crumple and then they don't end up apart from each other. They did bounce, I guess, technically, but that would be a start apart, end apart, but now there definitely would be deformation. And the idea of how we differentiate between, or how we determine, I said that again, how we determine which one it is really comes to that kinetic energy piece. And we'll get to that, but we aren't gonna get to that for a couple of days, okay? So that's to come. From a conservation of momentum problem standpoint, you treat elastic the exact same as you treat a partially inelastic, okay? So they start apart, they end apart, we treat those the same. in all 4 of these types, we have momentum being conserved, which means we can use the conservation of momentum equation. So on the worksheet in class momentum, we're going to work through 3 problems. The first one is question number 3, and I didn't realize till after I printed it off that it didn't really, I was missing some information and I didn't actually ask the question that I really wanted to. So I apologize, but I'm going to make some quick edits to what the question actually asks. So in question number 3, it talks about a 80-kilogram astronaut is floating in space repairing a satellite. The repair is complete, so she radios the shuttle and tells them to initiate the startup sequence to return to Earth. When she pulls on the tether, which is just a fancy word for a rope that they attach themselves into so they can reel themselves in, it was somehow cut and she was unable to pull herself in. Armed only with a 1 kilogram space wrench, she throws it as hard as she can, 5 meters per second. That's a very important number I forgot to include. 5 meters per second, hoping she will drift back to the shuttle in time. That's kind of like the example of the medicine ball on the ice, right? If I take the medicine ball and I throw it that way, I should drift slowly backwards on a frictionless surface, which space is a frictionless surface. So she's hoping to do that with her space wrench. Which direction should she throw the wrench? And then I'm just going to cross off that entire thing that was listed. That's a Fab 5 problem. In order to do the Fab 5 problem, we first have to do a conservation of momentum problem. Once we have the conservation of momentum problem, then we can do the Fab 5. I'm more interested in the conservation of momentum than I am with the follow-up calculation of the Fab 5. So the question I want to ask is not will she make it in time, is how fast will she move towards the shuttle? If I take a wrench and I throw it that way, I'm going to slowly drift in the opposite direction. So how fast will she actually be moving towards the space shuttle is the actual the calculation that I'm going to ask us to solve. Okay, so with problems like this, I strongly encourage you to draw a picture. So I kind of did it ahead of time. On that one, I drew boxes, but I could attempt, I'm not sure if I'm going to, but I could attempt a little fancier picture than boxes, but I'm not sure if I will. Oh, sure, why not? So here is the astronaut with her helmet on, and she has a space wrench in her hand. Okay, and now what happened is there was this rope, but the rope got cut. It was tethered. So if we were floating in water, right, and we want to get closer to shore, we can swim. We can swim through the water. And that causes us to move. But the reason that causes us to move is because we're physically pushing against water. Okay? An astronaut floating in the space shuttle can swim through the air, right? They could go like this, and they're pushing against air, which would then create friction, which would allow them to move. However, she's not in the space shuttle, she's floating in outer space, and there's no air particles. So does going like this do anything for an astronaut floating in space? No. Okay? So different movies have kind of solved this problem differently. We're going to use a space wrench that she has. In The Martian, Matt Damon poked a hole in a spacesuit in the palm of his hand, and he Iron Man did, I think, is that what he called it? Right, so he had air shooting out as like a jet to push himself towards the spacecraft that was coming towards them. In the movie Gravity with Sandra Bullock, she used a fire extinguisher to propel herself through space. She doesn't have that. She has a wrench. So the idea, though, is if my space shuttle is over here somewhere, she has 2 choices. She can throw, well, I guess she has lots of choices of which direction, but does she throw the wrench at the space shuttle, or does she throw in the opposite direction of the space shuttle? Which way do you think she should throw the wrench? Towards the shuttle, or away from the space shuttle? away, right? Because then she should drift towards it. Now, what the other option would be is like, well, if I'm not making it back, then no one's making it back, and it's not being a team play. Okay, so if she's going to try to go that way, then what she has to do is she has to throw the wrench the opposite direction. Same thing with that medicine ball example. If I'm gonna take the medicine ball and I'm gonna throw it that way, frictionless surface, I would slowly be drifting backwards. That's the same idea. So that's my before picture. That's my location 1. My squiggly line to show like, hey, a collision or an interaction has just occurred. And now we have our space wrench and my astronaut are now separate. So based upon my amazing drawing, what kind of collision would you refer to this according to that little blue sheet that you just have? Recoil, very good, very good. Okay, so they started together, her and the wrench start together, and they end apart. Now we're going to use this conservation of momentum. Our equation for momentum, P is equal to M times V. We're going to use that equation a lot. So if we just kind of I often call these like objects A and object B. So for each object, I need a mass. So if we call the wrench mass object A, we need the mass of object A, and we need the astronaut's mass, so the mass of object B. We're going to be determining momentum, so we also need to know the velocity of object A at location 2, after she throws her wrench at location 2, and we're going to need to know the velocity of the astronaut at location 2, so VB2. Now that's going to be equal to conservation of momentum is equal to my momentum before. So I also need to determine the momentum of her and the wrench. So if I call the wrench object A and I call her object B, then very creatively I refer to her and the wrench as object AB because they are together as one. So I'm going to need to know the mass of object AB, which is her and the wrench, and the velocity of her and the wrench before she throws the wrench, so VAB1. Now, we are going to solve single variable algebra. So of these 6 terms that I just listed, this is, by drawing a picture and labeling it like this, in my opinion, it builds this equation nicely for you. In order to solve for one of these, we need to know 5 of the 6, all except for 1. So if there's something you say, hey, I had too many variables, something's implied or you missed something. So the question that I ultimately wrote in is how fast will she be drifting back to the space shuttle? So what is her velocity after she throws the wrench? That's ultimately what we are solving for. Now, I'll fill in some of this information for you. The wrench was 1 kilogram. She was 80 kilograms. So collectively, when she's holding the wrench, they have a mass of 81 kilograms. We had to add it because I forgot it when I wrote it initially, that she has a velocity of 5 meters per second. Now, if you're watching this video and you're looking at the PDF that's linked, I think I fixed it on your document. Now, it's implied she's on a spacewalk, she's floating, she's working on a satellite, now she's got to go back. We're going to say that she starts with 0 velocity. The conservation of momentum equation says that the sum of my momentum before the interaction is equal to the sum of my momentum after the interaction. So the idea is if I start with 1 object before, I have 1 momentum. When I end up, I have 2 objects, which means I have 2 momentums that I have to sum, I have to add them together. Momentum is nothing more than mass times velocity. So when, like I was saying, if you draw a picture like this and you label this, I feel like it kind of builds the equation. You're gonna go mass times velocity of the objects we start with is equal to the momentum of this, so mass times velocity of this object, plus the momentum of this of mass times velocity. So it's really, I kind of almost think it's like, that squiggly line is kind of like an equal sign, and because I have two objects, it's kind of like a plus sign. Now there is one thing that I do not have labeled properly in my variable term. Does anybody see what I have improperly labeled or improperly, it's not 100% accurate. And I'll give you a clue, it has to deal with something that is a vector quantity. That object needs to have a -5. How do I know that the wrench is moving to the left and not right? Because it doesn't say to the left versus the right. You're right. It doesn't. I drew the picture that it's going to the left. If you drew the picture such that it was moving to the right, then your velocity would be positive. When I solve for my velocity of the astronaut, it's going to be positive. If yours were switched, then her velocity would be negative. So just something to keep in mind. So when we go through and we use conservation of momentum says the sum of all my momentum before is equal to the sum of all my momentum after. How many objects do I start with? Well, I start with one. So that means I'm going to have to find the momentum of that one object, which I called object AB, before the interaction. So P, momentum of object AB, one before. And that's equal to the sum of my momentum after she throws a wrench. So I have two objects, so I'm going to need the momentum of object A after she throws it, so PA2, and it's the sum of, so I'm going to add the other object's momentum, which is PB2, the momentum of object 2 after the interaction, or after the collision. Remember, our equation for momentum is mass times velocity. That's why I put mass and velocity. So PAB1 is simply taking the mass of object AB times the velocity of object AB before the collision or interaction. That's what the momentum of AB before is. And that's equal to the momentum of object A after the mass of A times the velocity of A after. Momentum is mass times velocity. So if I want the momentum of A, m times mass of A times velocity of A. And if I want the momentum after, then I got to make sure I use velocity of object A at location 2. Plus, momentum of object B is mass of B times the velocity of object B before. Again, by drawing the picture the way I did, with the labels that I do, with the variables that I have, this really just becomes this times this equals this times this plus this times this. So drawing a picture, really, really a good idea, in my opinion. Now, this velocity at location 1 was 0, which means they start with no momentum. So 0 is equal to the mass of the wrench times the velocity of the wrench, which is -5, because I drew it going to the left, so it's a negative, plus the mass of the astronaut times VB2. 0 is equal to -5 plus 80 VB2. Add 5 to both sides. 5 is equal to 80 VB2. Divide both sides by 80. VB2 is 0.0625 meters per second. space shuttle, but not very fast. Right around 6 centimeters or so. Now the original question was, hey, 15 meters, 5 minutes, will she make it? The answer was, yeah, she makes it in like 4 minutes, I think is what the answer would be. Conservation of momentum, the sum of all my momentum before is equal to the sum of all my momentum after. Okay? Draw a picture, label masses and velocity for each object at each location. And then once you have that done, I feel like these problems kind of go pretty well from there. All right, the next problem on that worksheet is number 6, found on the back. A 10,000 kilogram semi is sitting at a stoplight. A person driving their 2,000 kilogram car is looking at their phone and it doesn't see the semi stop. If the car was initially moving at 12 meters per second and they locked bumpers, I'm doing this one because in your homework you'll have one where 2 cars lock their bumpers. How fast do the car and semi move after the collision? So if we say I have a car that is moving to the right, okay, and it hits a semi which is stationary. They lock bumpers, which means they stick together. Based upon our little green sheet, what kind of problem is this? This is an inelastic collision. So once we've identified that we have we start with 2 objects, and we end with 1 object, then we can go through and add masses and velocities for each thing. By doing so, I feel like it really kind of forces you to look for those objects, which is going to be necessary to do a momentum equation. So, how fast will they move afterwards? We're solving for that VAB2. It says the car has a mass of 2,000 kilograms. How do I know that's a car? Because the car is moving. And the semi has a mass of 10,000 kilograms. So if they lock bumpers, they're essentially one 12,000 kilogram object afterwards. It says the car is initially moving at 12 meters per second. Now the way I drew it in my picture is to the right, which means it's a positive. Now you don't need the positive, I'm just kind of putting it there to kind of emphasize that point. And we're trying to solve for that. So that's all every number from my problem, but I'm missing the initial velocity of the semi. And that's not a number that was listed with a numerical value, it was a number that was given by a word. And what is my VB1? How fast is the semi initially going?
0.
Because it's sitting at a stoplight, right? So it's 0. So once we have all that, sum of all my momentum before is equal to the sum of all my momentum after. Mass times velocity plus mass times velocity is equal to mass times velocity. That's what's going to happen here. So I have 2 objects before, so because I have 2 objects before, I have to have 2 momentums before. Momentum for object A at location 1, and the momentum of object B at location 1. And we end up with 1, so I'm going to end up with 1 momentum afterwards. So they stick together as object AB, so I call that the momentum of object AB after the collision, so I call that location 2. I probably should have added that to my picture. Location 1, location number 2. Momentum. mass times velocity, mass times velocity, mass times velocity, mass times velocity. So if we're trying to find the momentum of this thing before, we take mass times the velocity of this thing before. If I want to find the momentum of this, I take the mass times velocity of this. That's why I list it the way I list it. So momentum of object A at location 1 is mass of A times velocity of A at location 1, plus mass of B times the velocity of B at location 1, right? Mass times velocity. Which is equal to momentum, which is mass of AB, times the velocity of AB after the collision. The initial velocity of the semi was 0 because it was sitting at a stoplight, which means it has no momentum to start. So when we plug in numbers, we get 2,000 times 12 plus 0. You don't need it, I know, you can leave it out, is equal to 12,000 VAB2. So what we're left with is 24,000 is equal to 12,000 VAB2. Divide both sides by 12,000. VAB2 is equal to 2 meters per second. So the semi is going to start to move because it just got smacked by a car, and the car is going to go slower because it's now moving a heavier object. We call that an inelastic collision. That's number 6. Before I erase that, I'm going to talk about number 7. Number 7, again, kind of a quick edit to number 7. Number 7 is a problem where in order to do the calculation, the momentum calculation, we'd have to do a conservation of energy, and ME1 equals ME2 problem first. I'll kind of talk you through it. I'll just say, hey, but if we did it, this would be the problem. I'm not going to spend the time doing the conservation of mechanical energy problem, but we'll talk about it. So we have an 80 kilogram student decides to go tubing in their backyard down a 5 meter tall frictionless hill. There's no work in, there's no work done by friction, therefore it can be an ME1 equals ME2 problem. Since the parents are concerned about her safety, they put a 40 kilogram hay bale at the bottom to stop her before she collides with a tree. If the hay bale does in fact stop her, how fast will the hay bale fly off? And then what type of collision? So what type of collision? I'm not going to address that right now because it's one of the last two. It's either an elastic or a partially elastic. The idea is she starts on the top of a 5 meter tall hill, right? And I'm just going to go through and I'm going to say, and then she's going to go down, right? So she's going to end up down here and she's going to be moving like this. We could solve this problem by doing an ME1 is equal to ME2. I'm not going to spend the time to solve this problem doing an ME1 equals ME2, but the idea is at the top she only has gravitational potential energy. At the bottom of the hill she only has kinetic energy. And when we go through and we'd solve, we would find that she has a velocity of 9.9 meters per second. Okay? So in reality, we would have had to have done that calculation first to then do the momentum equation. On your homework for tonight or tomorrow's virtual day, you do not have any where you have to do ME1 equals ME2. That's also why I'm kind of fast forwarding past that part. But what we are dealing with is we are dealing with her running into a hay bale. Okay, she is going to be moving towards that hay bale at location 1. That's the collision piece we are going to deal with. And then after, what we're trying to do is we're going to have to figure out how fast that hay bale goes moving. So she is moving separate from the hay bale, so they start apart. So we need the mass of her, mass of A, times the velocity of her before, so VA1. We need the mass of the hay bale, and how fast that hay bale was moving before she runs into it. Then she hits the hay bale. So we need to know her mass and her velocity after. And the hay bale goes flying away, so we need to know the mass of the hay bale and the velocity of the hay bale after. Now notice with the masses, I don't go like MA1 and MA2. And the reason I don't deal with that is I'm assuming like she didn't drop a mitten and lose some mass. Or she didn't lose her scarf, or the tube, or a limb. The idea is her mass is going to stay relatively constant, right? So I just call her the mass of object A. And I believe the problem says that she has a mass of 80 kilograms. It also says, well, I would have had to calculate it, that initially she's moving at 9.9 meters per second. That's how fast she's going. She went down the hill, she's now going 9.9 meters per second. Oh, watch out, right behind that hay bale is a tree, which we don't really care about for our drawing, but that's why the hay bale's there. Okay, so there's that tree. But the hay bale is in front of that tree, which has a mass, has a mass of 40, and is sitting in front of the hay bale. I'm sorry, it's sitting on the ground. After she hits the hay bale, assuming it didn't, like pieces of straw or hay didn't go flying everywhere, it's still going to have a mass of 40, and we're going to try to calculate how fast that hay bale flies off. Now the one number that I didn't fill in is what is her final velocity? And it says in the problem that if in fact the hay bale does stop her, then she would have a VA2 that's equal to 0. That's a number that was given, implied, not implied, is given in the problem. This was given as a word instead of a number. Okay, so sum of all my momentum before is equal to the sum of all my momentum after. I start with two objects, so I need to start with two momentums, PA1 and PB1. And that equals the momentum, sum of my momentum after. I have two objects after, so that means I have to have two momentums after. Momentum is mass times velocity, so mass of A times the velocity of A before, plus momentum of B before is mass of B times the velocity of B before, which equals the momentum of A after, so mass of A, velocity of A after, plus the momentum of B after, mass of B, velocity of B after. Now, in this particular problem, we have two different things that have velocities of 0. The hay bale starts with 0 velocity, therefore 0 momentum, and she ends up with 0 velocity, so therefore she ends up with 0 momentum. So what we're left with is an equation that is the mass of her, which is 80, times 9.9, which is 792, which is equal to 40 VB2. Divide both sides by 40, and we get a VB2 of 19.8 meters per second, which is right around like 40 some miles per hour. So that hay bale's moving pretty good. You ought to not get hit by that hay bale. Okay? I know we're getting to that time. I just wanted, there's a homework sheet that I just set out called Momentum and Collision. I want to just really briefly talk. There's two sides to it. The front side is dealing with one object, so change in momentum, momentum impulse theorem. The back problem, the back side of that worksheet has three calculations. They are conservation of momentum equations, just like we did today. There's a recoil, there's an inelastic, and then there's a start apart, end apart. We can't answer what type of collision this is at this point. For this one is one of those last two, and I'm not asking collision types. So the front side is the momentum impulse theorem, delta P is equal to F times delta T, one object. The back three problems are conservation of momentum equations. So there's one here or one there on that desk. That's your virtual day assignment for tomorrow.